Okay, this is a continuation of a base plate discussion. This is a spreadsheet that we have right now to do base plate design. The first tab here is actually basically reactions from SAP. So you get the shear, axial, left column, right column. So right now it's set up obviously just for two columns, and we have this coming over. It's linked to the SAP template right now, but you need to update this all the time. So anything that's in blue is, and my thing is, you need to update. Anything in red is calculated. So I'll show you a legend later. So blue numbers are user input, red numbers are calculated, black is pretty much you don't really need to touch, it's default whatever to whatever it is, and then the pink or brown, whatever it's output from either Visual Basic or VLOOKUP function. So you can see all these are black, red, green is linked. It's linked from another file. So so when you go down on it, I don't need to worry about anything else. I just need to fill out the one cells that are in blue. Okay, so the design guide, this one is based on design guide 1 and design guide 16. So I separate into left column and right column. The only difference is because the reactions are different for each column. So this one essentially it is a VLOOKUP for these two. So I change it to combo 1. These numbers change. Okay, and when I'm doing the evaluation, it all depends on what that load. So let's go back to, let's say, 55 and 62 or 65 is okay. 62 is probably high shear and axial. Okay, the base plate design data is we're using grade 50, so that you don't need to change that. 50 is the KSI, is the FY. Phi B is 0.9. B and N are the plate width. Okay, thickness, again, when you see that, that's a user input field.
It's in the set we model like a pin.
Yeah, we model it as a pin model. But that's why when you look at output, you don't have any moment. You only see V and P, so there's no M. So if we do model that as a pin or as a moment, then you have another column to come in to worry about the plate. So right now the base plate is designed as a pin only. Okay, so these are the geometry of the base plate: thickness, width, and length. This is the geometry of the column. All these will change based on the column size. So this one you could type in, or you could make it a drop down based on the AISC column if you want. Okay, so 14 by 53, we could do the 16 by 57 is one of our size. So you can see all these should be updated and to reflect the new geometry. Okay, for the weld, we are always doing 70 KSI as the electrode strength. Phi factor is 0.75. The weld size and number of size, those you could adjust if you want, but the default is 1/4 inch both sides you weld it to. Okay, so that's the welds for the base plate. Anchor bolts is 3/4 or 7/8. So this one is 7/8. So I think we only have a couple of them, and I have a new one that does drop down in terms of what that's based on. So if I do 0.75, then somewhere down the road would change. No, this is an outdated one, I guess. There's one I have a drop down that drops it and changes the effective area. So that one needs to be updated. So I'll give you the updated one. Okay, so that should change. The area should change based on the diameter of the bolt here, obviously. Okay, so right now this one didn't change, but going to the next components, you have the concrete, you have the concrete bearing factor, and all these equations now, concrete bearing A1, A2, FP, these are the per design guide 1. Like I said, all these are based on uniform bearing pressure, and that's why you see the capacity is so high because is V, V sub P is 175. So when you look at it, is the DCR for this combination is only 0.154. Okay, so that's plate, the concrete bearing plate yielding. Remember, ours cantilevers out a little bit because the cantilever is so little. You're going to get a very high capacity on your design. Okay, so this one is again, the DCR is very low. So once we take care of the compression design, I was going to go to tension, but sometimes I needed some information from the well design first. So I went into do the well design. So this is the column welding to the base plate. What kind of welds we need and what checks are we doing. So I'm checking the shear only, tension only, and I'm doing combined shear and tension for the two. Okay, so these are the weld sizes and the weld capacity. I'll give you a MathCAD file that's easier to follow, like that later. So I have that as a checker. So check shear, tension, and tension only each check. Okay, after the weld has been designed, and the weld here is this. The weld size is just a VLOOKUP from what you specified on top here already. So you don't need to change it down there. Like I say, all the changes should be just up front. Everything after that is just calculation based on those numbers. So you don't need to look into anything down here if you don't have to. Okay. Some of them now, after the like I said, the weld, then you do the tension design. The tension design, we're doing it per design guide 16. We want to capture the two-way bending behavior, because that would give us higher capacity and more true performance of what the base plate would be. Okay, so what we do is we actually compare that to some rocking moment, because when you test it, you see the base plate, it's going to lift up on one side, it's going to compress on the other side, and then your anchors is going to be tension. So when you look at the frames, they don't just pull up. Okay, you don't just pull up, because you also have a shear component associated with that also. Okay, so that you're going to have a component. And my new figure, I have a new figure actually for this one that actually draws the tension and draws the shear, and it's on my desktop. I guess we're not looking at the latest one. So, but most of them stays the same. All we're trying to do is, okay, what kind of rocking moment due to my tension? Okay, once you calculate the rocking moment, then you calculate your capacity based on the geometry you have, based on the thickness of the plate, based on your layout of the anchor bolt. That would give you a Y, and you should go in and confirm what that is. So make sure is correct. So I see one number 190 divided by 2. That's not. I need to look in what that is. So you get a Y, basically a yield line vector, and then you get a plate thickness that's required. This equation is very similar to our step 18 of the column flange check when we're doing the column flange yielding. Okay, so after that we do our anchor bolt design here as well. So the anchor bolt design, we have the phi factor, we have the seismic factor, and we also have the grout. For ACI 318, if you're on top of a grout, then you have to take 20% off the shear capacity. So we have to times the capacity by 0.8 instead of 1. So what that does is reduce your capacity in shear by 20%. Okay. Now we have to check what I did is shear only, tension only, and then combine shear and tension for the anchor bolt check. Okay. Anchor bolt check here is something that we discussed before. We want to check the plate yielding prior to anchor bolt yield, if possible. Right? We want the anchor bolts to be strong. I don't want it to yield. So here are the capacity. Yeah.
Why would Technicon be holding Butler to a 1/32nd tolerance on base plate holes? Isn't it an 8?
On base plate hold tolerance,
Yeah.
it's oversized, but all the hole tolerance should be 1/32.
It's 1/32.
Yeah, all the tolerance should be that. We ask them to oversize it already. I don't want them to oversize more.
So I wonder if they're bigger or smaller than what he's doing.
Yeah, we have that. Typically, they allow you to go 1/32 over what that 1/16.
Right.
So
what size should the hole? It should be one.
What size are we?
16/16, right?
What size is it?
It's like they're probably. I think they're 12s.
Are they fabricating something?
Yeah, and Technicon's rejecting them because they said that they're more than 1/32 out. It's that frame that everybody's waiting on.
If they ask us, let them submit it to us and we'll review it, because typically our holes are oversized already.
Right. So if they're going beyond that, that's the...
Right. So in that time, if they want to weld a washer plate to take care of it, if that's faster. I don't know. At this time,
what would I worry about? They used their anchorage or not? I think they did. So it should be okay.
Yeah, the holes, it's already been oversized for 1/16. They cannot go over that dimension by another 1/32. So, okay, base plate. Okay, so base plate discussion. That's what that was. Okay, so all the bolt holes are oversized by 1/16. Okay, your base plate is allowed to be more than that. However, you have to do something to accommodate that if you make it too big. Okay, so our inspector is actually rejecting it because they're going over more than what's allowed. So what's allowed is typically 1/32 over the 1/16. So a vendor for that frame is actually they have bigger size, more. So our inspector is rejecting. Okay. So that's base plate related, fabrication wise. So okay, what do you have now is, like I say, this is the checking the plate with yield before the anchor bolts with yield. Okay, so if for the whatever condition per se, if during a big earthquake we want something, if something's gonna yield, we want that to be outside of the concrete. So if they have to replace it, they can replace it. We don't want them to have to replace the bolt, right? So that's why this is the checking to make sure. So I would start, when you guys' solution, make sure you use, I would say, high strength bolts if possible to start. And start with 3/4 high strength bolts and check this. No, you or not. If you use a low strength bolt, okay, you'll see that the plate the anchor bolt is gonna yield before your base plate does. And this is just our self-imposing requirement. Is not in the code. Okay, but we're thinking if you have to replace it, you should do the plate that's outside if you have to, whereas you have to dig out the concrete and replace the bolt. Okay, so this is one thing. So what this now on the column DCR does is we are taking all these loads, iterating it from 1 through 64, or actually 1/36 to 64 is the design combo. 1 through 35 are the ASD combos we don't use for design. So if you look at it, when you return DCR, all it does is looping through the calculation for all of them and returning the DCR. So let me go do that right now quickly to see how quick that is, just to do something like this. Okay, anchorage DCR. Let's do, I think, the base plate DCR. Left column. Okay, my worksheet is left column base plate. Left column base plate. Okay, come back to here. Range, select. I want to clear the contact. So each time I'm clearing these output first. Okay, so that will be F something to J154. So I'm clearing the content, and then from there on I go from I to 36 to 64. Okay, by changing the F12 field. So I is F12. You can see this is F12 by changing this one. I'm changing this one. Okay, so if I change this one, what happens? If we go 34, these VLOOKUP is based on that one. So my force changes. So now the force changes, my DCR is going to change. So if that's what's happening, then I'm first is checking a DCR on the concrete, taking a DCR in compression, and then I'm returning the maximum one. So at the end, I am just taking some of the DCR values and returning it to these fields here. And once I return it, basically I do one for the bearing, one for the plate, one for the well, one for tension, one for anchor bolt, and do it once and hit return, and it'll do it all the time. And then on the bottom I'm summarizing, getting the maximum DCR. Okay, so that is for all the base plate check. So right column is very similar. Instead of the forces here, I'm looking up a different column of forces for the right column, and essentially everything else is the same. Okay, so that's base plate design. For now, we are doing it. So what you don't see here is the bearing check on that bearing check. Now that's the component that I'll probably add in next to check that we are not crushing the grout too much. Okay, because when we saw testing, first mode is probably grout crushing. Okay, the concrete capacity right now we assume to be only 25 PS, 2500 psi. Our grout we require a minimum of 5,000. So we do have a minimum required, so I could check it to a higher value instead of a lower value. So the area is going to be less, but my allowable stress probably more. So we'll see what happens. But I'll add that into this base plate spreadsheet, and then when you guys take it and modify to whatever you need, then at least you have the bearing on the, underneath this component when you're looking at. So that will be the next improvement on the pin base design. Okay, and when we get to the future work, then we'll have to include it. So, and when we model, learn SAP tomorrow, I'll show you guys how to model the pin and the base as well. If you get the chance to do a pin on the base.
But you say that the blade must be used before the anchor bolt.
Yeah.
But assuming the maximum DCR is the DCR of the anchor bolt is the most is the biggest. It's bigger than the DCR of the blade. So then maybe the anchor bolt will be used before.
Let me